Hello everyone, and welcome. I'm excited to kick off this presentation on topographical surveying. Today, we'll explore contouring, understand the characteristics and uses of contours, and learn how to read maps effectively. Over the next few slides, we'll cover these key topics to give you a solid foundation in topographical surveying. Let's get started. Topographical surveying is a crucial process we use to identify and understand the natural features of a country. When we talk about topography, we're referring to the physical landscape, things like hills, valleys, rivers, and forests. This survey helps us create detailed maps that show these features clearly. For example, on this map, you can see the hills and valleys that shape the terrain, along with rivers that flow through the land. It also marks the locations of villages, towns, and forests. These details are essential for a variety of purposes, from planning infrastructure to understanding environmental conditions. Overall, topographical surveying provides a comprehensive view of a country's physical landscape, which is fundamental when making decisions related to development, conservation, or navigation. It helps us see the big picture of how the land is shaped and how different natural features are interconnected. This slide doesn't contain enough information. That's why we're moving to the next slide. Contouring is essentially a type of leveling operation, and you'll notice that the equipment used for contouring is quite similar to what we use for leveling. The main goal here is to identify points on the ground that share the same reduced level, which helps us understand the terrain better. These points are then connected through contour lines, which either join points of equal elevation or are created using interpolation techniques when the data isn't directly available. These contour lines are very valuable because they reveal the topographical features of the ground, like hills, valleys, and slopes. By comparing different contour lines at various elevations within a closed area, we can get a detailed picture of the terrain. This information is crucial because it allows us to perform accurate calculations for engineering projects, whether it's designing roads, drainage systems, or other infrastructure. So, in essence, contouring helps us translate the physical shape of the land into a usable, visual format that supports our planning and development efforts. Let's talk about contour lines. These are the lines you see on a map where the surface intersects with the ground surface, and they help us visualize the terrain. You can think of a contour line as a line passing through points that all share the same reduced level, or RL. For instance, a contour line marked 100 meters indicates that every point along that line is exactly 100 meters above a reference level, usually sea level. Similarly, a contour of 99 meters means all those points are at 99 meters RL. Now, when we look at a map that shows only these contour lines for an area, we call it a contour map. It's a powerful tool because it allows us to understand the elevation changes and the shape of the land without seeing the actual ground. In the context of our overall theme, which is understanding terrain and landforms, contour lines help us interpret the landscape's elevation and slope intuitively. They are fundamental in fields like surveying, civil engineering, and geography, making complex terrain features easier to analyze and work with. Let's talk about the contour interval. The contour interval is simply the vertical distance between two consecutive contour lines on a map. Think of it as the elevation difference between those lines. For example, if you have contour lines at 100 meters, 98 meters, and 96 meters, then the contour interval here is 2 meters. Now, this interval isn't fixed. It actually depends on a few key factors. First, the nature of the ground matters. A flat area might have a larger contour interval, say 10 meters, because the elevation changes are minimal. Conversely, a steep area would require smaller intervals, like 2 meters or even less, to accurately depict the terrain. Second, the scale of the map influences the contour interval. A large-scale map, which covers a smaller area in more detail, will typically have a smaller contour interval. Meanwhile, a smaller-scale map might use larger intervals to keep things simple and clear. And third, the purpose of the survey itself plays a role. If we're planning a detailed engineering project, we'll want a smaller interval for precision. But for a general overview or regional planning, a larger interval might suffice. So, in essence, the contour interval helps us understand the terrain's relief, but it's adaptable depending on the ground, the map's scale, and what we need the map for. When we talk about contour interval, it's important to understand that it varies depending on the nature of the terrain. In flat country, for example, the contour intervals are usually quite small, like 0.25 meters, 0.5 meters, or 0.75 meters. This small spacing helps us see even slight elevation changes. On the other hand, in hilly or steep areas, the contour intervals tend to be larger, such as 5 meters, 10 meters, or even 15 meters. This makes sense because the elevation changes more rapidly, so we don't need as many lines to represent those changes clearly. Another key point is scale. For small-scale maps, which cover larger areas, the contour interval might be around 1 meter, 2 meters, or 3 meters. Conversely, for large-scale maps that show detailed, localized areas, the contour intervals are often smaller, like 0.25 meters, 0.5 meters, or 0.75 meters. It's also crucial to remember that once a contour interval is chosen for a particular map, it remains constant throughout that map. This consistency helps us interpret the terrain accurately across the entire map. So, understanding the appropriate contour interval based on terrain and map scale is fundamental for reading and creating reliable topographic maps. Let's talk about the horizontal equivalent. This is the horizontal distance between any two consecutive contours on a map. It's an important concept because it helps us understand the spacing of contour lines. Now, what's interesting is that this distance isn't always the same. It actually varies depending on how steep the ground is. For example, on steep slopes, you'll notice that the contour lines are very close together. This indicates a rapid change in elevation over a short distance. Conversely, on flatter terrain, the contour lines are spaced farther apart, showing a gentle slope. Recognizing this variation is key when interpreting topographical maps, as it gives us clues about the terrain's steepness and overall shape. So, understanding the horizontal equivalent helps us better analyze the land's features and plan accordingly. When we look at a general map of a country, it typically shows us the locations of roads, railways, rivers, villages, towns, and similar features. But as useful as these maps are, they don't really give us any information about the nature of the ground surface itself. And that's where the challenge comes in. For many engineering projects, whether we're planning roads, railways, or other infrastructure, we need to understand the terrain more deeply. We need to know how the ground surface looks and behaves because this information helps us decide the best alignments for construction and also allows us to estimate the volume of earth that needs to be moved or excavated. This is precisely why contour maps are so important. They provide a detailed representation of the ground surface, which is essential for successful project planning and execution. That's why, in the context of engineering, preparing a contour map is a critical step. It gives us the detailed terrain information we need to make informed decisions and to ensure our projects are both efficient and effective. Now let's look at the various uses of contour maps. First, they help us understand the nature of the ground surface of a country. By studying a contour map, we can get a clear picture of the terrain, which allows us to demarcate the most feasible routes for communication, whether it's roads, railways, or pipelines, connecting different places efficiently. Next, when planning engineering projects, contour maps are invaluable for selecting suitable sites or determining the most economical alignment. This helps us save costs and ensure safety. They also allow us to approximate the capacity of reservoirs or the area of catchment zones, which is crucial for water resource management. Another important use is establishing the intervisibility between different points, knowing which locations can see each other, which is especially useful for planning communication towers or viewpoints. Contour maps also assist in marking out routes that follow a specific gradient, which is vital for transportation and construction purposes. Furthermore, we can draw cross-sections of the ground surface in any direction directly from the contour map, giving us detailed insights into the terrain's profile. Lastly, they enable us to estimate earthwork quantities, like how much material needs to be excavated or filled, making planning and budgeting much more accurate. In essence, contour maps are versatile tools that support various aspects of planning, engineering, and resource management, tying directly into the overall theme of understanding and utilizing the terrain effectively. Let's talk about the characteristics of contour lines. You'll notice that near the top of a hill or higher ground, the contour lines are very close together. This indicates a steep slope as you approach the peak. On the other hand, near the foot of the hill, the lines are wider apart, showing a gentler, flatter slope. So, the spacing of these lines really helps us understand the steepness of the terrain. Closer lines mean a steeper slope, and wider lines mean a more gradual incline. Recognizing these patterns is essential for interpreting the landscape and understanding the terrain's shape. Now, let's take a closer look at the characteristics of contour lines. You'll notice that near the bank of a pond or a depression, the contour lines are much closer together. This indicates that the slope in that area is quite steep. As you move away from the bank toward the center, the lines spread apart, which tells us that the slope becomes more gentle or flatter. So, essentially, the closeness of the contour lines helps us understand the steepness of the terrain. Closer lines mean a steeper slope, and wider apart lines indicate a flatter area. Recognizing these patterns is crucial when analyzing landforms and understanding the overall topography. Now, let's take a closer look at the characteristics of contours. When contour lines are evenly spaced, they indicate a uniform slope across that area. This means the terrain is gradually inclining or declining, without sudden changes. You can see in this example how the spacing between the lines remains consistent. The numbers, like 100, 99.5, 99, and 98.5, represent elevation levels. The regular spacing of these lines helps us quickly understand the slope's uniformity and how the land gradually changes elevation. Recognizing these patterns is crucial for interpreting terrain features accurately, whether for construction, navigation, or environmental studies. It's a simple yet powerful way to visualize the landscape's shape at a glance. Contour lines always form a closed circuit, which is a key characteristic. This means that no matter where you look on a topographic map, the lines will loop back on themselves, creating a complete boundary. It's important to remember that these lines can be found either within the limits of the map or even outside the map's boundary, depending on the area being represented. This closed-loop nature helps us understand the elevation changes and the shape of the terrain more clearly. It's a fundamental concept because it allows us to interpret the landscape accurately, whether we're dealing with hills, valleys, or other landforms. So, when you see these contour lines, think of them as self-contained circuits that give us a comprehensive picture of the terrain's relief. Let's talk about one of the key characteristics of contour lines. Normally, contour lines cannot cross each other because that would imply a place where two different elevations meet at the same point, which isn't possible on a landscape. However, there is an exception to this rule. If you have an overhanging cliff, the contour lines can appear to cross. In such cases, the overlapping part must be shown using a dotted line to indicate that it's a feature that extends over the edge. This helps us accurately represent complex landforms while maintaining the integrity of the contour map. Understanding this characteristic is essential for interpreting topographic maps correctly, especially when dealing with intricate terrain features. Let's take a closer look at the characteristics of contours. When we see higher values inside a loop, it typically indicates the presence of ridge lines. Think of these as elongated features that run perpendicular to the contour lines at right angles. Recognizing this pattern helps us interpret the terrain or data features more accurately. Essentially, understanding where the higher values are located relative to the contours allows us to identify key landforms or data trends more effectively. This concept fits into the larger picture of how contours help us visualize and analyze spatial information in a meaningful way. Now, let's talk about one of the key characteristics of contours. When you see lower elevation values inside a loop on a map, it actually indicates a valley line. And what's interesting is that this valley line runs perpendicular to the contour lines. So, essentially, the contours form a sort of enclosure, and the lowest points are inside that loop, highlighting the presence of a valley. Recognizing this pattern is crucial because it helps us understand the terrain's shape and how water might flow through the landscape. It's a great example of how contour lines can reveal the underlying topography and guide us in interpreting the terrain more accurately. Now, let's talk about the characteristics of contours, specifically when we see a series of closed contours on a map. These closed loops are quite significant because they always indicate either a depression or a summit. The key difference lies in the values inside those loops. If the values decrease as we move inward, meaning the lower values are inside the loop, it's indicating a depression. On the other hand, if the values increase inward with higher values inside the loop, then that loop represents a summit. Recognizing this pattern is crucial because it helps us interpret the terrain's shape and elevation changes accurately. This understanding ties directly into our overall goal of analyzing landscape features through contour maps, allowing us to identify high points and low points effectively. Now, let's move on to an interesting feature of contours. When we look at the depressions that occur between summits, these are actually called saddles. Think of a saddle on a horse. It's a low point between two higher areas. Similarly, in topography, these saddles represent the lowest points between two peaks or summits. Recognizing these features helps us understand the shape of the land and how different elevations are connected. This concept is important because it gives us insight into the landscape's form and can be crucial in fields like geology, cartography, and even outdoor navigation. So, understanding these depressions or saddles adds another layer to our overall comprehension of contour characteristics. Now, let's take a closer look at the characteristics of contour lines. One key point to remember is that when contour lines meet at a single point, it actually indicates a vertical cliff. This is an important detail because it tells us about the steepness of the terrain. Unlike gentle slopes where contour lines are spaced out here, the lines converge at a sharp angle, showing a sudden drop-off. So, if you see several lines coming together at one point, you can interpret that as a cliff or a steep drop. Recognizing this helps us understand the terrain better and interpret maps more accurately. It's a crucial concept that ties into how we read and analyze topographical features across different landscapes. Today, we'll be discussing methods of contouring, which are essential in accurate land surveying and mapping. There are two main methods, the direct method and the indirect method. Let's focus on the direct method first. This approach is quite straightforward, but depends on the specific characteristics of the area we're working with. Now, within the direct method, there are two cases to consider. The first one is when the area is oblong in shape and can't be controlled effectively from a single station. In such cases, we need to take multiple readings from different stations to accurately map the contour lines. The second case is when the area is small and can be controlled from a single station. Here, the process becomes simpler, as a single station can provide all the necessary data to draw the contours. Understanding these cases helps us determine the best approach for precise contour mapping, which is vital for projects like land development, drainage design, or any civil engineering work. Let's talk about the direct method of contouring, specifically when the area we are working with is oblong and can't be effectively controlled from a single station. In this case, we identify various points along the contour on the ground by taking level measurements. These points are then marked with pegs, which helps us visualize the contour more clearly. Once marked, we plot these points onto a map using a suitable scale with a plane table. It's important to note that this method, while very accurate, is quite slow and tedious because of the detailed work involved. However, the precision it provides in drawing the contour lines makes it valuable, especially in situations where accuracy is critical. Overall, this method emphasizes meticulous groundwork and careful plotting to achieve reliable contour mapping. Let's discuss the direct method of contouring. Specifically case I this applies when the area we're working with is oblong and can't be easily controlled from a single station. In such cases, we start by locating various points along the desired contour on the ground using precise level measurements. These points are then marked with pegs for easy identification. Once marked, we plot these points on a map, choosing a suitable scale, using a plane table. It's important to note that this method is quite slow and requires patience because of the detailed work involved. However, the key advantage is that it provides very accurate contour lines, which is crucial for detailed surveys. So, while it may be time-consuming, its accuracy makes it a valuable method in specific situations. Today, I'll be discussing the methods of contouring, starting with the direct method. When the area we're working with is small and can be effectively controlled from a single station, this is the approach we use. In such cases, the radial line method is adopted to create the contour map. Now, while this method is indeed quite slow and requires a lot of patience, it has the advantage of providing very accurate, actual contour lines. So, even though it might be tedious, it's highly reliable for small, manageable areas where precision is key. This method ties into the overall theme of choosing the right technique based on the specific project needs, balancing effort and accuracy. Now, let's talk about the indirect method of contouring. In this approach, we start by taking reduced levels, or spot levels, of different points at regular intervals along a series of lines set up on the ground. Think of these lines as our reference paths across the terrain. We then plot these points on a sheet, choosing a suitable scale to accurately represent the area. The spot levels are carefully noted at each point, which forms the basis for our contour lines. Next, we determine the points of the contour lines by interpolation. That means we estimate the positions of these lines between our known points, based on the levels we've recorded. Once we have these estimated points, we join them to create the required contour lines. This method is quite quick, making it efficient for initial surveys, but it's important to note that it only provides approximate locations of the contours. Additionally, there are two ways to adopt this method. First, through cross-sections, where we look at slices of the terrain, and second, through the square method, which involves dividing the area into square sections for more systematic plotting. Overall, this indirect approach offers a balance between speed and approximate accuracy, fitting well into our overall survey planning. In this slide, we're looking at the indirect method, specifically using cross-sections to determine ground levels. The first key point is that we start with a baseline, center line, or profile line, which serves as our reference. Then, at regular intervals, say every 50 or 100 meters, we take cross-sections that are perpendicular to this line. Along each cross-section, points are marked at consistent intervals, like every 5 or 10 meters, to help us plot the terrain accurately. A temporary benchmark is established near the site to provide a fixed reference point for elevation measurements. Next, staff readings are taken along the baseline and across the cross-sections, and these readings are carefully recorded in the level book. It's important to mention both the baseline and the cross-sections in your records for clarity. From these readings, we calculate the reduced levels, or RLs, for each of the marked points. Once we have the RLs, we plot the baseline and the cross-sections to a suitable scale on paper or a map. After plotting, we note the RLs of all the points on the map, which allows us to interpolate and draw the contour lines. This method is especially useful for route surveys when the cross-sections are taken transverse to the main longitudinal section, giving us a clear picture of the terrain. In summary, it's a systematic way to determine ground levels indirectly, making it practical for larger or more complex sites. Let's now look at the indirect method, specifically using a cross-section. This approach involves examining a cross-section of the object or structure we're interested in. By analyzing this cross-section, we can gather valuable information about the internal features without having to look at the entire object. It's a very useful technique because it allows us to interpret data from a slice, giving us insights that might be hidden from surface observations alone. The key here is understanding that the cross-section provides a snapshot of the internal structure, which can be crucial for accurate analysis. This method is particularly helpful when direct measurement isn't feasible, and it helps us connect the internal details to the overall context of our project or study. So, using cross-sections effectively is a fundamental part of the indirect method in our toolkit. Let's talk about the indirect method, specifically the use of squares. In this approach, we divide the entire area into a series of squares. The size of these squares is quite flexible and depends on the nature and extent of the ground we're working with. Typically, the sides of these squares range from about 5 to 20 meters. To keep track of everything, we number the corners of each square in a sequence, like 1, 2, 3, and so on. Next, we set up a temporary benchmark near the site to serve as a reference point, and we also establish a level at a suitable position to measure elevations accurately. Using a leveling staff, we take readings at each corner of the squares and record these in the level book, making sure to note the serial number of each corner for clarity. Once we have all the staff readings, we calculate the reduced levels, or RLs, for each corner. These RLs give us the elevation at each point. Then, we plot the skeletons of the squares to a scale that suits our project. After plotting, we note down the RLs at each corner. The final step is drawing the contour lines, which we do by interpolating between the RLs. This process helps us visualize the terrain's shape and elevation smoothly and accurately. Overall, this method is efficient for mapping uneven ground, especially when combined with precise measurement and plotting techniques. It connects the physical measurements to a detailed representation of the terrain, which is essential for planning and design work. Let's talk about the indirect method, specifically the approach using squares. In this method, we divide the entire area into a series of squares. The size of these squares isn't fixed. It depends on the nature and extent of the ground we're working with. Typically, the sides of these squares range from about 5 to 20 meters. To keep track of everything, we number the corners of each square serially, like 1, 2, 3, and so on. Next, we set up a temporary benchmark near the site, which acts as our reference point. We also establish a level at a suitable position to measure height differences accurately. Then, we take staff readings at each corner of the squares and record these values in our level book, making sure to follow the sequence of corner numbers. Once we have these readings, we calculate the reduced levels, or RLs, of all the corners. Using these RLs, we plot the skeletons of the squares on a suitable scale. After plotting, we note the RLs at each corner, and then we draw the contour lines by interpolating between these points. This method provides an efficient way to map out the terrain's elevation, especially over larger or irregular areas, by breaking it down into manageable, measurable sections. Let's talk about the method of interpolation of contours. Essentially, this process involves locating the contour line proportionally between the plotted points. So, when we have 2 points, say A and B, we can determine where the contour line falls between them based on their RL values. For example, if the RL at point A is 98.75 meters, and at point B is 100.75 meters, and the horizontal distance between these points is 10 meters, we can see that the vertical difference is 2 meters. Now, suppose we need to find the location of a contour line at 99 meters RL. The difference between 99 and 98.75 is 0.25 meters. To find the position of this contour line, we calculate how far along the line from it to be it should be. We do this by multiplying the total distance, which is 10 meters, by the ratio of the RL difference, which is 0.25 meters, over the total RL difference between A and B, which is 2 meters. So 10 divided by 2 multiplied by 0.25 gives us 1.25 meters. This 1.25 meters is the distance from point A to the contour line, measured along the same scale used for plotting the points. By plotting this distance from A, we can accurately locate the 99-meter RL contour line. And of course, the same process can be repeated for other points to complete the contour line, ensuring that our contours are accurately proportioned between known points. This method of interpolation is fundamental in contour mapping, helping us draw smooth and precise lines that reflect the terrain's true shape. Let's take a look at this map. As you can see, it's a two-dimensional representation of the Earth's surface, and it uses graphics to effectively convey geographical information. Maps like these help us understand the exact location of features and how they relate to each other across the globe. Maps are truly fundamental to society. They're essential tools for navigation, planning, and understanding our environment. When we talk about creating maps, we refer to the field of cartography, which is both an art and a science. It involves the careful preparation and design of maps to ensure accuracy and clarity. In the past, cartography was mainly done through traditional manual methods, what we call conventional cartography. But today, this process is rapidly evolving. Computer-aided design and graphics now play a major role, and digital maps are replacing old paper maps. This shift is making maps more accessible, more detailed, and easier to update. Looking ahead, the exciting part is that technological advancements continue to push the boundaries of cartography. These innovations promise to bring even more sophisticated and user-friendly maps and related services that can serve society in better ways. So, as we move forward, the combination of technology and cartography will keep shaping how we understand and navigate our world. The size of the Earth is just too big to be represented accurately on a small map. To make it possible to show the whole Earth, or even parts of it, we use something called a scale. The scale is essentially the proportion we choose to relate distances on the map to distances in real life. It's like a ratio that helps us understand how much we've scaled down the actual size. The key point here is that the scale tells us the relationship between the distance you see on the map and the actual ground distance. So, when you look at a map, the scale helps you figure out how far apart things really are. This concept is fundamental because it connects the map to the real world, allowing us to interpret distances accurately. It's an essential part of understanding how maps work and how to use them effectively in our overall study of geography. When we talk about the representation of scale on a map, there are three main ways to depict it. The first way is through words, like saying 2 centimeters to the kilometer. This means that 2 centimeters on the map correspond to 1 kilometer in real life. It's a straightforward method, but it does have some limitations. For example, because it's expressed in words, it requires some mathematical calculations to understand actual distances. Plus, different countries use different units of length, so a scale written this way might not be immediately clear or easily understood by people from other regions. So, while this method is simple, it's important to be aware of these potential drawbacks, especially when sharing maps across different audiences or international contexts. Let's talk about the representative fraction, or RF for short. It's expressed as a fraction, like 1 over 50,000. Now, if the scale is 1/50,000, what does that mean? It means that 1 unit of measurement on the map corresponds to 50,000 units on the ground. This is why it's also called the numerical scale. Here's an important point. The distances on the map and on the ground need to be measured in the same units of length for this scale to work properly. One of the great advantages of the representative fraction is its flexibility. It can be read in different units of length. For example, if you see a map with a 1/50,000 scale and measure a distance of 1 centimeter on the map, that would represent 50,000 centimeters on the ground. Alternatively, if you're working in feet, then 1 foot on the ground would correspond to 50,000 feet on the map. This makes the representative fraction a very versatile tool because it allows you to convert measurements easily, regardless of the units you're working with. It's a fundamental concept because it forms the basis for understanding how maps represent real-world distances, helping us interpret spatial data accurately. Now let's take a closer look at the graphic scale, which is shown here as a strip divided into equal parts. This kind of scale is also known as a plane scale or linear scale. Essentially, it's a visual tool that helps us understand the real-world distances represented on a map. For example, if we look at this particular scale, it indicates that each division on the strip corresponds to 10 kilometers on the ground. So, when you measure a distance on the map using this scale, you can directly convert it into actual ground distance. One of the key advantages of using a graphic or linear scale is that it maintains its proportionality regardless of whether the map is enlarged or reduced. This means if you zoom in or out, the scale still accurately represents the real-world distances, which makes it a very reliable tool for map reading and analysis. So, in the context of our overall presentation, understanding this scale helps us accurately interpret distances on maps, which is crucial for navigation, planning, and geographic analysis. When we talk about a qualitative nomenclature used to describe the relative scale of a map, we mainly refer to whether the map is considered small or large scale. These terms help us understand the general characteristics of the map without getting into precise measurements. A large-scale map, for instance, covers a smaller area, but it provides a lot of detail. You can see individual objects clearly because they are represented as larger, more distinguishable features. This makes large-scale maps ideal for detailed planning or navigation in a localized area. On the other hand, a small-scale map covers a much larger area, but with fewer details. The objects appear smaller, and the map is less detailed overall. These maps are great when you need a broad overview, such as for regional or national planning, where detail is less critical than geographic scope. The key point to remember is that large-scale maps are more detailed, but cover less ground, while small-scale maps cover more area, but with less detail. This distinction is fundamental as it influences how we interpret and use different maps depending on our needs, whether focusing on local details or understanding a large geographic region. Let's talk about topographic indexing. The Survey of India is responsible for producing the topographic maps of our country. These maps come in different scales, which helps us understand various levels of detail. Now, to easily identify a specific map of a particular area, the Survey of India has adopted a systematic numbering system. When we look at the international series of maps, covering the region between 4 degrees N and 40 degrees N latitude, and 44 degrees E to 124 degrees E longitude, they consider the 1,000,000 scale map as the base map. This map essentially provides a broad overview of a large area. The base map is divided into sections, each measuring 4 degrees of latitude by 4 degrees of longitude. These sections are then numbered sequentially from 1 to 136. It's important to note that this numbering covers only land areas, ignoring water bodies. This indexing system helps in quick identification and retrieval of maps, especially when dealing with such vast regions. It ties into our overall understanding of how detailed mapping and geographic organization work, making navigation and study much more efficient. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's take a closer look at how these sections are organized on the map. Each section is divided into 16 smaller parts, arranged in a grid of 4 rows and 4 columns. Now, each of these sections covers an area of 1 degree of latitude by 1 degree of longitude. This precise division allows us to analyze the region in a very detailed way. Starting from the northwest corner, the sections are numbered and organized in a specific sequence. They run column-wise, that is, from top to bottom within each column, and then move across from west to east, ending in the southeast. This systematic approach helps us understand the spatial distribution more clearly and ensures consistency in how we analyze each part of the region. By breaking down the area into these manageable sections, we can better interpret patterns, identify trends, and make informed decisions based on the data collected from each grid. This grid-based division is fundamental for detailed spatial analysis and helps connect the overall theme of our presentation, understanding geographic variability, by providing a structured way to look at complex data. Now, let's take a closer look at how these 1 degrees by 1 degrees sheets are subdivided. Each of these larger grid sections is divided into 4 smaller parts, which helps us analyze the data in more detail. These smaller sections are each 30 minutes of latitude by 30 minutes of longitude. To keep track of them easily, we assign cardinal directions, NE, NW, SE, and SW. This division is really important because it allows us to pinpoint specific areas within each larger grid, giving us a more precise understanding of the spatial distribution. Connecting this to our overall theme, This subdivision technique enhances our ability to analyze geographic data with greater accuracy, which is essential for the detailed insights we're aiming to achieve. Now, let's look at how the 1 degrees by 1 degrees sheets can be further subdivided. Each of these larger sheets can actually be divided into 16 smaller sections. These sections are defined by 15-minute segments of latitude and longitude, creating a finer grid within each degree. What's really useful here is that these 16 sections are numbered from 1 to 16 in a columned manner, meaning they are arranged vertically. This systematic numbering helps us identify and locate specific areas more precisely within each larger sheet. Understanding this subdivision is crucial because it allows for more detailed geographic analysis and data collection. It also facilitates better accuracy in mapping and in various applications like navigation and spatial planning. So, in essence, this layered approach, degrees, then sections, then subdivision into smaller parts, enhances our ability to organize and interpret geographical information effectively, tying back into the overall theme of precise and systematic geographic referencing. Now, let's look at how a 15 by 15-foot sheet can be subdivided for better handling or analysis. Essentially, this large sheet can be divided into 4 smaller sheets, each measuring 7.5 feet on each side. These smaller sheets are typically labeled as NW, NE, SW, and SE, which stand for Northwest, Northeast, Southwest, and Southeast. This division makes it easier to manage, analyze, or even transport sections of the sheet individually. It's a simple yet effective way to break down a larger area into manageable parts, tying into the overall theme of efficient planning and resource allocation. Remember, understanding these subdivisions helps in precise measurement, easier handling, and better organization in our projects.